A magnitude 3.4 earthquake just struck the Netherlands, and yet, despite its small magnitude, it led to several hundred reports of damage. This even included more than a dozen possible reports of damage significant enough that a structure may no longer be safe to reside in. You might be wondering how on earth such a tiny earthquake caused such significant damage, but if you live in or just east of Groningen in the Netherlands, you are already well aware of this problem. As, since at least the 1990s, earthquake damage from more than 1,000 earthquakes has resulted in at least 80,000 instances of damage, totaling by some estimates a cost of more than 2 billion euros. And yet, none of these earthquakes were any larger than a magnitude 3.6, something that traditionally is considered too small to cause structural damage. Before I elaborate, I want to add an asterisk to the prior damage figure. You see, not all of the damage in this area was caused by just these earthquakes, as much of it was instead triggered by ground subsidence. This ground subsidence, which is as high as 8 mm a year, is caused by the same reason that generated these earthquakes. As these earthquakes were deemed to be induced or caused directly or indirectly by human activity, albeit not intentionally, due to natural gas extraction in the Groningen gas field. These earthquakes occurred in part due to the removal of large volumes of natural gas which beforehand occupied a portion of rock below ground. Once removed, with an estimated 84% of the natural gas in this vast natural gas field having already been extracted, there was nothing to replace the locations where the natural gas originally was, so the rock above the natural gas deposits began to subside. This removal also changed the pore stress of the underlying rock, and just like what can happen due to the creation of a large open pit mine, it resulted in the activation of fault lines that were previously partially held in place and mostly prevented from slipping via the existence and mass of the natural gas. It is an accepted fact that a large number of regional earthquakes within or just outside of the gas field were induced via this process, with a total of 1,770 suspected induced earthquakes having been triggered since 1991. Using earthquake data from KNMI at this website, which by the way is not directly involved in this derivative work nor necessarily endorse what I have done with their data, I have created this seismic chart showing the rising and declining induced earthquake rate over time. I included suspected induced earthquakes within the Groningen gas field or within 10 kilometers of its edge. Do note that the number of earthquakes large enough to be potentially felt, in other words magnitude 2 or larger, dropped after the first government policy change in 2014, which resulted in an immediate 80% reduction in natural gas extraction. In 2018, there was a further change as natural gas extraction was continuously decreased year over year until 2023 when extraction completely ceased altogether. While some residents thought that complete cessation of natural gas extraction will result in the number of potentially damaging earthquakes to immediately or quite quickly drop to zero, this is not the case. Don't get me wrong, seismic activity has notably dropped since its peak in 2017, reaching near 2004 levels in 2025. These numbers should further decrease over time, but the problem is that subsidence in induced seismicity will likely continue for at least another few decades. So, why was the damage from these earthquakes so severe in some cases? After all, the statistical average damage claim involved a total upwards of 10,000 euros. The answer involved a multitude of factors. In Europe, the most susceptible building type to earthquake damage is composed of unreinforced brick, as you can see in the simulation during purely hypothetical earthquake ground motion equivalent to 0.25 Gs. Factor 2 is the area's geology. Any soils that contain abundant sedimentary particles such as sand, silt, and clay cause seismic waves that pass through them to slow down and thus increase in amplitude, while also causing them to reflect off of the many particles at a higher rate than compared to, say, solid granite. As a result, earthquake damage is naturally amplified on these soils, and a combination of the aforementioned sediments is what structures in the vicinity are built on top of. The third factor is that many pre-existing structures are quite old and are thus more susceptible to earthquake damage. Thankfully, over time, many regional structures are being upgraded to withstand future potential earthquake damage. As a final note, I would like to thank my new YouTube channel member Sue Munzen Meyer for supporting my work.